So welcome everybody to this webinar, Design for Reliability of Electronic Devices with Ansys, of course. The duration of this webinar will be 1 hour, but first let me go over a little bit of the logistics of this webinar. As you can see, you have a small interface where you can adjust your settings for audio. If you do not see it, that little red arrow will give you more options. In that view, you will also have a questions pane where you can fill out your questions anytime during the webinar. And at the end of the webinar, we will have a Q&A with all the questions that have been asked. During the webinar, you will be muted, so don't worry about that. But at the end, everyone will be unmuted, so you can also give additional reply to your question. So for the webinar of today, I'm joined by my two colleagues, Edwin and Tim, who are Senior Account Manager and Technical Solutions Consultant, and they will explain you a lot more that you may not have known about reliability today. This is a short agenda for today, and we will start with the introduction of Infinite and Ansys by Edwin. Edwin, I will give you control.
Thank you, Sarah. Yeah, welcome everybody to the Electronics Reliability webinar for today. First of all, I wanted to give you a short introduction of Infinite. If you are not yet familiar with Infinite, we are the Ansys lead channel partner and doing this for over 30 years now. And this contains the distribution of the Ansys software, also the support, organizing trainings and giving consultancy, depending on the complexity of the Ansys analysis. I think my slide is not moving. Oh, there it is. Yeah, Ansys is longer than Infinite on the market, over 50 years now. We are the industry leader, the most used simulation software. It's our core business, so that's the only thing we do, everything which is related to simulation. And of course, the size of the company gives us a unique position for further growth. If you look at simulation over the years, things have changed. In the past, simulation was more like a control tool. You design something and you want to know if it did what you thought it would do. But nowadays, even at the ideation phase, at the conceptual phase, you can use Ansys, for instance, like Ansys Discovery, to invest if one design parameter does a better job than another one, and that can be everything, materials or parameters. After that, you go more into depth in your design and analysis, and especially to know exactly what's going to happen, and with the result of that, reduce your development time and also get away from warranty costs. Also, there are some new solutions in the manufacturing. So this means that you can now simulate, for instance, the printing process. So the thing you print is exactly what you had in thought. And last, and that's a thing where you see a lot of development nowadays, is the operations to reduce your maintenance costs. And that's mainly done by using a digital twin. And to give you a better idea what is a digital twin, over here you see an example of a relay and an Ansys Maxwell magnetic simulation. And this is an example from Venus Contact. At the right side, you see a multi-domain system where several analyses are part of that domain. And the thing is, for instance, when you have a relay, it's hard to predict when it fails, and that can be because of the wear of a sensor. But to make a multi-domain system from your total system, and then instead of assume data, use really data from out the product which is placed at your customer. You can sensor, for instance, the loads and temperatures, and then you have a better understanding what's really going to happen. So the result is that you can lowering the unplanned downtime of the total system, which can save you, of course, lots of money and also reliability to your customer. Over the years, Ansys expanded quite a lot regarding the solutions they have to offer. Also the industries we serve, like aerospace, automotive, energy, high tech. And today it's more about high tech. We have solutions in all fields, for instance, electro and also electromechanical fluids, all type of coupled physics, and some new things about photonics and safety systems, and everything is combined together. Now, I don't have the time to really go in depth, but today, if we look at the total product portfolio of Ansys, we are focusing on the electronics part. What do we mean with design for reliability? So why is it so important to be reliable? Nowadays, you see an increase of number of new features with more advanced electronics. You want to lower, of course, your bill of material costs, accelerate to your market faster, and of course, very important, improving the first pass yield. So not have a lot of dropouts during your design process, and decreasing the warranty rate, and all those things are getting more and more important because the reliability is critical for all types of industries and technology trends. So if you look at the old way of working, sort of a trial and error way of working, you design, you build, you test. Now it doesn't, you have faults, you fix it, test it again over and over. And a lot of your development costs are placed in this procedure, and there you can improve some time and also costs. The thing is that if you look at the requirements nowadays for the electronics reliability, there are higher demands on performance regarding power, high speed, in 112 gigabits per second, and also the lifespan demands were higher, over 10 years nowadays. Also the place where your products has to perform, temperatures, EMI, EMC, but also the mechanical reliability. There are much more demands than in the past, and of course the costs which are involved you want to lower, and especially you want to decrease the amounts of defects and also your manufacturing costs. So how can we quantify when you use simulation? What can that mean for you? Especially when you look at the system level side for thermal simulation. The example I showed from Phoenix, where you have a total system where you use reduced order models to speed things up. You get a much quicker understanding what's really happening with your product on the market, and of course also to decrease the development time for your hardware design, and of course finally also because of lesser prototypes to lower your material costs. So in this example, if you look at your product reliability and your operational performance, demand's getting higher. So you have to look at your demands and meet or exceed, for instance, the power and signal integrity goals, and minimize the EMI, EMC risks. But also you have to optimize your strategies for cooling, so you get a better performance. And of course, things can drop, can shock, so you have to be aware of that and simulate that also, so you don't have problems when they are out on the market, your products. Also the robustness of your design, and material and manufacturing variations get more and more. And of course, you want to minimize with system integration, assembly, and product transportation risks. Now, if we look over here, and the software is used a lot in the electronic market, for instance, Qualcomm as a company, which developed the chips for the smartphones, and everybody knows that temperature is an issue. So how lower the temperatures, how better it performs, and also the lifespan will be increased. So that's what Qualcomm does with the portfolio of Ansys. And also at NXP, the systems getting smaller, they interact with each other on the IC level. So you want to know exactly what's going to happen. And in this case, Ansys Q3D is used for that, and Ansys Red Hawk for designing the chips. So finally, the key results is once again reduce design time, reduce costs, and get a more qualitative, better, and reliable product. Ansys is used a lot in the high-tech industry. Like 97% of the 500 high-tech companies use Ansys, but also a lot of smaller companies and also startup companies and academical users are using Ansys for these purposes. But of course, also not only worldwide, also in the Benelux, we already have a large number of customers using those tools. So now I give the word to Tim. He will go a bit more in depth and is going to tell you something about the design for reliability. Okay, the words to you, Tim.
Thank you, Edwin. Okay, so let's dive into the design for reliability and then understand like what are those aspects that we want to focus on. So here we can see that reliability itself actually comes with a lot of different aspects. When we're talking about electronics, the first thing we usually talk about is the electrical reliability, but there are also some other aspects that is rather important that we like to focus on. So first, maybe a more introduction about electrical reliability. Electrical reliability, of course, we are talking about signal integrity and power integrity, or SIMPI. In this case, we want to know that if the signal is still nice after some certain transmission, if there's any interference, and how we're going to shield them, how we're going to place the decoupling capacitors, things like that we do on our PCB boards or even inside of a chip. Then we have thermal reliability. That is when the device gets smaller and smaller nowadays, thermal issues becomes more and more pronounced, that even affects our electrical performance. And even if it doesn't affect our electrical performance too much, you still don't want a hot spot on a particular point of your PCB board. So that is the moment that thermal reliability becomes more important, that you want to think about how you can tackle with your thermal issues, how you're going to dissipate your heat from a single point, maybe from on top of the chips, towards a more uniform environment. Mechanical reliability, it's essential to like the reliability of your device itself, because like your device, you're going to undergo a lot of different thermal conditions and thermal cycles, and this will of course affecting its mechanical reliability over time when there's a mismatching in thermal expansion coefficient. On top of that, we are also having some portable devices that we're going to bring it on a different environment. That means vibrations are going to introduce, sometimes even drop-in will happen. And you think about drop-in, that's actually a very, very huge G that those devices are going to experiencing a large accelerations. So how are we going to conform with these design goals and then propose our electronics device to a more extreme conditions that is always a very challenging issue. Now, you think about all things come together, then we have more comprehensive multiphysics. That is, we not just focus on the electrical or thermal or mechanical, but actually they interact with each other, as I already briefly mentioned, that we have some electrical arrangements, then you see some kind of concentration of our currents that, of course, generating some kind of like hot spots on our PCB board on a certain traces, and these traces we want to dissipate its heat, but how we're going to dissipate the heat, and also if the heat was not dissipated successfully, how it will actually causing the mechanical failure. And also it's not just one-way coupling, but also this can be a two-way coupling. We'll talk about that later as well. So this is the more multiphysics comprehension for multiphysics reliability analysis. But last but not the least is we call it reliability physics analysis. The reliability physics analysis is a very, very unique tool that you don't find anywhere in the other tools on the market, because it gives you the full understanding of how your tool going to survive over your operation time. So for instance, we have the different sources that can affect our lifetime. We have vibrations, we have thermal cycles, and also there are different let's say different parts, different combinations, soldering techniques, and also how we could package our chips on top of the PCB boards. All these factors comes together, and it's inherently very, very complicated. We are talking about hundreds of parts, thousands of traces on top of a PCB board, and how we're going to get an overview of them. And that's when this reliability physics analysis comes in. And this, we have a special tool called Ansys Sherlock. So here's the overview of what I just go through. There's a multi-domain challenge in design for reliability.
I think it's good to know what our audience thinks of this and how they are working with this. So we have a small question for you. I think you can see it right now. So in which fields are you and your company doing design for reliability? Of course, it can be the case that there's none of the above, but Tim will go over the options.
Yeah, so if you are doing PISI nowadays, then that's definitely electrical. By the way, this is multiple choice. So if you and your organization is doing already looking into thermal and structural analysis, thinking about how you're going to improve your design so that you can have a better reliability outcome, then that's the second one. And of course, multiphysics, we're really talking about the coupling between electrical and thermal and structural analysis. So that is not just doing one physics, but also consider the different physics are going to affect your individual physics. So that's the multiphysics. And the full lifetime prediction, it can be any kind of lifetime prediction, but how confident can you tell for your device going to survive, for your design going to survive? How are you going to decide the warranty to your customer, saying that this is going to be 10 years, this is going to be 20 years? What kind of analysis, what physical data are you based upon? Those are we call for lifetime prediction.
So I see that some people have already voted. Let's just wait a little bit, a couple of more seconds. Okay, I'm gonna close it and let's look at the results. Oh, just a second.
Yes.
There we go. So most of you are in electrical.
Yes, so we apparently have 1/3, 2/3 of our audience is already doing electrical, being the most important one. That's where our design starts. Thermal structure, of course, that's really important. I'm actually very happy to see some of the audience is already doing multiphysics considerations, and even a quarter of us are doing full lifetime prediction. But let's diving into these topics, especially I want to dive into the thermal structure, multiphysics, and for lifetime prediction, because those are, as we can see, less people are doing now, and then let's understand why they are so important for our success of our design.
Perfect.
Thank
Let's
you,
continue.
Sarah. Okay, so as I said, let's dive into thermal reliability first and see what kind of challenges we have and also how we're going to tackle with them from the Ansys tools. If we look into thermal issues, there are some issues that's very, very critical to solve. Like you can see there's some kind of like burnout here because of the high power concentration points. There are always some hotspots. There are some traces that we don't know if they are big enough. If we want to make it larger so that we reduce the concentration of the power losses, or if we are going to avoid of having too much unnecessary capacitive effect. So these thermal issues are can be from the chip die domain all the way to a very large system level, even the entire data center level. And all of them are actually be able to be tackled, be analyzed in Ansys tool. That particular Ansys tool is IcePack. But also if you are doing the chip level, then that's Red Hawk, that you can help you to understand inside the chip how the thermal going to distribute it and how you're going to improve your design. We're going to spend a little bit more time on IcePack because it handles much wider specs, especially starting from the chip package all the way till the a full data center. So if we look at chip package, then how are you going to package it? Are you going to place them? And then also more importantly is that how the thermal going to distribute it to your eventually the connection arrays of your chips. And usually the most efficient, like inside the chip, it's definitely going to be way too complicated to simulate. So what we do is that we can actually simply extract such a thermal circuit, as you can see over here. Now, using the thermal circuit, we'll be able to describe the chip performance as a single object, and then be able to quickly get to know how it will interact with the environment. Then we go to the PCB level. So PCB level, of course, the most challenging one is once again being the complicated traces on our PCB boards. And if you think about that, if you want to build everything in a simulator, it might cost you days to run. However, in IcePack, we could actually just map in those traces back on the board and changing the conduction coefficients. As you can see, the 3 different directions of conduction coefficients of a single board. And actually this can be layer by layer. For instance, like dielectric layer, we don't have a very strong conduction coefficient except those vias. And then this gives us a very, very high accurate thermal distribution on a board. And then we know that IcePack is a full CFD solver. That means we do not just have the thermal distribution without air, but we do also see how it interacts with the air around it. Then we can decide how we're going to cool our boards using different cooling strategy. So this really gives you already a tremendous amount of valuable insights on how are you going to tackle with thermal issues and how you can improve them, but maybe by just separating your devices, or maybe just thinking about like how are you going to changing the dimension of your heat sinks. And when we're talking about changing dimension of heat sinks, that's of course more like the entire electronic system level, because in our entire electronic systems, then you have maybe more than one PCB boards, then we are encapsulated into, for instance, into a case, and then they are interacting with the environment as well. We have some motors, of course, that like it itself has multiple coils inside, and then also how are you going to dissipate its heat to the outdoor environments. here we have also maybe a cassette of entire a server that you see how the airflow flows in and how the air gets heated up by then, and maybe how you're going to tackle with your thermal management along the different drive cycles. So you have some high loads and low loads, how you're going to manage them so that you get a more stable state, a stable performance. And that's actually what I just mentioned, dynamic thermal management. Like we have the temperature going up as maybe this is the idle that you just start your machine, and then there's a high like usage scenario that you then the temperature goes high in general, and then maybe we're doing something else, then it's more down to the idle level. And this kind of dynamic or like the entire load cycles is crucial, because then we know that when we're trying to overshoot or trying to turbo boost our of our performance, how much time can we do that? And if we cannot do that, how are we going to downgrade our operating frequency so that we can still perform reasonably well while we avoid any thermal issues? And these kind of things we can couple together with the system level analysis. So one of the major solutions from iSpec is that we able to generate this reduced order model. Then the reduced order model can take into account of your different thermal power generations, different flow conditions, and eventually you'll be able to simulate this thermal system level thermal response in just a matter of seconds. So here we see that a box can also have some kind of networking that we can extract. So here we have the PC desktop, a server. Then we can have some nodes, thermal nodes inside, and then easily extract the thermal circuits. Also, same thing for liquid cooled plates. This is going to be also helps a lot in putting into our system circuits and understand our thermal management system behaviors. Now, iSpecs being the very powerful CFD solver, helping you to solve all kind of thermal issues. It also have a very good connection with all different types of tools. It consumes the network, the thermal network from the chip level. It interact with the it also consumes the thermal losses, or we say the electric losses, ohmic loss, for instance, from different electromagnetic simulation tools in Ansys, putting it into iSpec. Of course, if you are doing different electromagnetic simulation, a third-party one can also be properly prepared and then put it into iSpec for mapping the thermal the loss on your traces and on your systems. Then on top, once it generates the thermal maps, then it can send to mechanical or Sherlock or even generate a reduced order model so that we can use in Ansys Twin Builder or other network simulation tools such as MATLAB, Simulink. So this is like full coupling towards the upstream FEA tools, electromagnetics, and then we have CFD tools handle with thermal issues, and eventually passing it to the structure and more system level connections for full system response. So that's a short summary about thermal reliability. Start with accurate thermal models, and then we can consume the ECAD and MCAD, and know that those two types of different CADs, that's the EDA layout and also the mechanical geometry, they comes together and then really in a single system to be able to give you a very accurate result, but while it's super efficient. And its efficiency is always the heart of Ansys tools, that it's all like in the industry, we're always talking about faster time to the market. And that's why Ansys has invested so much in trying to get your result as soon as possible. And therefore, to do so, we combine the best of technology like reduce order model, like the CAD integration, trace mapping techniques to help you to achieve that. Now, with that being said, we can further looking into mechanical reliability. And it's actually a very, very interesting topic because there are so much mechanical failure that happen in such a small spaces in PCB boards and chip packages that will be eventually very crucial to your product reliability. So the physics is essentially quite complex because we are dealing with all kinds of different materials, different structure comes together, and then there are thermal issues, there are shocks, vibration, jumps, and impacts, and there are even also humidities and other more miscellaneous factors that could cause our lifetime to reduce. So we have to think about how we're going to model our PCB in a very efficient way. Now we can of course put everything in a homogeneous piece of solids, but that's apparently not going to be very accurate. So we can start to think about divided by layer, but there's no trace information. So nowadays we have some areas that's very dense in traces, then that in that area we'll have high conductivity. Then this is why the trace mapping becomes very important, that to be able to get an accurate results using trace mapping techniques. Now, trace mapping, you will notice that it does not change the mesh. It does not induce anything, a new structure. What it really does is to changing your material properties at the local location of your elements. As you can imagine, then you lose the interaction between the traces and also the boards. So that's why since 2020 R2, or since last year, Ansys has incorporated this new innovation that will now be able to really bring in the traces, but we don't really bring in the traces as a real solid element inside, because then we really enter into the final stage, which is called trace modeling. But what we do is that we actually use them as a reinforced elements. So those reinforced elements going to interact with our solid elements, that's our boards. That is going to help us to conduction the heat. It's going to help. It's going to cause some interaction between the different thermal coefficients. However, the mesh does not become over complicated, and there's no contact element needed between the reinforced element and the solid element. So trace reinforced approaches being one of the best between the speed and the accuracy. As you can see that the trace modeling approach, which really put everything as a solid, is most accurate, but you're definitely going to solve it not just in hours, but in days. However, the trace reinforcement approach can really bring your working time down to a daily working level, not like having only one simulation per day, but maybe multiple simulation per day to help you to understand how you can improve your design already. So this is, and still the impactful accuracy give you more insights between these traces and also the board's material inside the entire PCB board. We can also look into more down to the details, for instance, the heat sinks, the leases, and most important, the solder joints, and how we're going to have our solder arrays, and then which one is going to suffer most of the thermal stress and maybe accumulating strain, and how it will going to fail eventually. This is usually one of the weakest spots in our entire electronic devices. So solder joints, we're looking at fatigue and fracture, like how when you use over time, when it's going to fail, and also the solder reflowing process, like when you put the chips on top and then heat it up so that you're using a reflow to bind the soldering, like what might be the additional issues that it appeared, that how you're going to avoid your component failure when you during this refilling cooling process. And then we also have the tumble test, that to see how a device is going to survive in such a very violent shaking and impacting environment. And also the drop testing, of course. Drop testing, usually you maybe make some prototyping and then just send to the physical lab and testing. Now think about how much time it costs you and also how much money it costs you to just do a prototyping and do a drop testing. And thinking about if you can do a drop testing within just one day on your computer and then get the most valuable insights, knowing how you can improve your design. And that's actually the value that the simulation, and especially in this case, we are using explicit simulation to be able to give us and then tell us how we can move further to our design for reliability. And if you are doing packages, then there's moisture effects that you can also take into account, thinking about the moisture going to diffuse into your packages and how it will swell your structure as well. Oh, sorry, one slide's been jumped. So this is the reflow process, as you can see, modeled and simulated in Ansys Fluent. And then we also have the thermal issues, and then the package wrappage during the reflow process because of the mismatch of the thermal expansion coefficient. Now, putting everything together, we have electroanalysis sending us the DCIR information that we know, okay, so how much losses it's going to distribute, but it does not really tell us how the thermal going to distribute it because it also depending on the conduction coefficient on this board. And then so once we do that, we will be able to understand thermal analysis. And with that, we send the information and we can actually, it's the valuable thing is that once you know this thermal distribution and know the thermal expansion, you can also thinking about how are you going to mount your PCB boards? What's your mounting strategy? If your mounting is going to causing additional local stresses or not. So these kind of things are all crucial to your reliability issues. So we see deformations, we see the soldering bolts, and also how we can use submodeling to really capture down to the detail of the fatigue lifetime of our solder bolts. Now, looking at the entire structural domain, we see that the problem time magnitude from a very short impact to the long-term creep, a deformation because of thermal cycle. And then you see that they are all type of different solvers that Ansys is providing. In a quasi-static, static, and normal harmonic dynamics, we can easily do that in the implicit analysis. While when we're talking about drop testing and also like very high speed impacting, then we're talking about more explicit analysis, which is provided by Ansys Dyna, LS Dyna. Shock and vibration, more in model analysis or random vibration analysis, sending your vibration power distribution profiles in different your power distribution spectrum profile, and then knowing how your structure will going to vibrate and also how much it will survive over time using the fatigue techniques. Drops and impact, I think I already covered this part, so this is some more details. And also moisture effects. Once again, moisture effects is specifically for packagings that once we package stuffs, the moisture flows in, and then how it's going to distribute, diffuse into our solids, and then causing related stresses. Now, if you're looking into the delaminations and soldering joint fatigues, how your solder will going to crack over time, and how you're going to thinking about different strategy to improve them, then this is really down to the cracking analysis that we can do as well in Ansys tools. But more likely, we would like to looking from a more system level here. You see that the vibration fatigue, which part is going to have a lower lifetime, and how and then start to thinking about maybe different mounting strategies, maybe a different arrangement of your components to improve your lifetime. Water and contaminations, you want to conform with different IP standards, 65, 67, even 69, and then are going to do such kind of analysis to make sure that they are conform with standard before you send it to the test labs. Now we have some quick example here that we can see also flexible PCBs, how like the folding process, the manufacturing process, going to build up some plastic strand into your material, and this changing of plastic strand might also causing some change of our electrical and properties, and how are we going to predict that the potential issues, maybe when we have a short circuit or maybe when we have a system failure, thus this is going to be one of our most fragile components in our system. Flexible PCB as well, as we have now be able to have the flexible traces. That means we can even start to do a lot of different traces, as long as we have also reasonable components that can survive on this flexibility. And this is more and more has become a trend in our modern industry. As you can see, this is the simulation process that we have in Ansys mechanical, that we wrap it up and see how the thermal, the imported traces actually follows. And also by doing so, we were able to simulate the stress and strain because of the wrapping and changing of the geometry. Okay. So this is the mechanical reliability that we have covered. So they are drop test, shock test, and also vibration, long-term thermal cycles issues. These are all falling into our mechanical domain. Now they are, I want to take another 10 minutes to talk about, specific talk about Ansys Sherlock. Sherlock is a very dedicated a tool that is specific for reliability physics analysis. And we're talking about all different reliability issues coming from thermal cycle fatigue, solder reflow failures, a manufacturing process during the manufacturing and testing process, how much additional temperature you are going to introduce, additional vibration you're going to introduce, and then thereby even the shipping process, the storage conditions, how eventually it will affect your lifetime of your components. As you can see, these are all important factors. So it is eventually an FEA tool, very easy to set up. All you need to do is to bring in your ECAD layout, and then make sure the component and also prepare a component list and make sure the component are properly assigned. This usually will only take you a few hours for the first time, and then after that it will be only few minutes, even few seconds for the second or third time. Make sure that it is properly defined. Then before the end of the day, you already have your first prediction, even if this is the first time you're using this tool. And this prediction gives you the vibration fatigues, thermal cycling fatigues, and also the pass-through hole thermal cycling fatigues, and so on. So when do you like to implement Sherlock? Then maybe in the initial part selection, you want to find out which part will have a better lifetime, to which part is going to be your, let's say the weak spots of your entire PCB board, because the entire PCB board eventually works as a single system, and any a component failure causing the entire system fail. So find out where this weak spot is important. Then we think about how we're going to place it, because the part placement will cause eventually some of the parts, maybe you place them at the vibration, natural vibration that's very high, and some of the parts you can actually place them in the proper place, or if there's a specific spots you have high vibration deformations, then how are you going to improve your mounting strategy so that reducing the possibility of the parts failure because of replacement issues. And of course, eventually we're going to find our bill of materials and then also the final layout. We definitely like to thinking about design for manufacturing, knowing that we are actually doing so-called design for reliability process here. So Sherlock really democratized the FEA of FEA, let's say the complexity of FEA analysis for a electronics and mechanical engineer, particularly suitable for reliability control engineers, to doing a proper in-depth analysis while getting the results in a very short amount of time with a high confidence of your results, taking into account of mechanical, thermal issues, and also your part selections and layout design. So let's look at into a more clear detail so that give you an idea of why I believe this is so easy to use. So this is actually the beginning, that where you bring in your CAD. Once you bring in your EDA layout, it immediately get recognized by Sherlock, and then you can already see that all of the components, layout, and traces are imported. And of course, you probably will spend some time on make sure that the components are indeed the correct components. And then the next stage is becomes super easy because you just apply the loads, and then the loads when we're talking about is the real life loads. For instance, what are the random vibration profile of your when I say profile, I mean the spectrum of your board going to experiencing. What is the stages during the shipping process? What is stages during the inventory process, and also even the manufacturing process, and then eventually define the usage process. So it's really cover the entire product lifetime of the loads. And then we easily find out where the component fails. Like these two components apparently being very likely to fail, because even though they are not sitting in the highest load area. So how are we going to improve them so that we avoid this kind of failure in a certain time? Now, when we're talking about failure, not failure from day one, we're talking about failure after 4 or 5 years. How do you know each component will fail after 4 years or 8 years or 12 years? This kind of information is what Sherlock can give you. So here, this is another example interface that when we bring in the layout, it automatically recognizes a lot of components. Of course, some of them maybe there's some missing data, so that as an electronics engineer, we can easily filling in to make sure that everything is right. But the best part is that it already try to recognize what kind of material, what kind of component it is, and then give you some nice template that you can start with. And of course, there's a very, let's say, very comprehensive global parts library. You, as a company, you can also build your own company library on top of that, so that you can bring your most accurate component on the board. This is what I mentioned, life cycles, environment loadings, take into account of different stages. What are the thermal loadings? What are the harmonic vibration loadings, and even the shock loads? And you get a report like this. These red parts are going to fail because they cannot, eventually, they are not meeting our requirement, which is like 10% of the end product, or 10% possibility it will failed after 10 years. So if like 10% of a product failed after 4.5 years, then that's apparently not good enough, and eventually we're causing a lot of money on warranty issue. However, we don't want to build a super reliable electronics, then that's actually over design and making our design very costly. So what we want to do is to build just enough so that we can bring down the cost, make it more profitable, while in the meantime make sure our lowest cost of a warranty in the entire product lifetime. Here we see a simple example that we see. This is a 3D model, also easily generated by Sherlock. The only thing you need to do to get this is bring in your EDA layout, and that's it. Sherlock handle everything else for you, and then build. Of course, you can you have to input your shock profile, but there's also sample profile you can start with, and then you see your displacement plot, and eventually see which part is going to fail, and also what's the predicted lifetime. Automotive industries being one of the industry that requires a quite high standard for our electronic devices because of its usage scenario, several loads of thermal cyclings across the day, and then also in the entire year, different profiles. So how are you going to capture this, and knowing that your device can withstand such a thermal cycling, so that this is once again based on the fatigue model that we have, then we'll be able to predict the solder joint fatigue or breakthrough hole fatigue. Design for manufacturing, during the manufacturing process or testing process, that how this process is going to affect your devices, because we don't want the testing process and manufacturing process causing additional failure to our board. So this is also something very important that we can already think about. And eventually think about different packaging strategies. Maybe we change our pad sizes to make it pass, or maybe we're changing our packages to the other types of package so that we can also pass our criteria. Or maybe we just change our laminations, or maybe use a more expensive lamination materials so that eventually it passes. And of course, different strategy will cost different. And with that, you will have some very solid data help you to make the decision that which direction you want to go to meet the lowest cost while still meeting your goal. So once again, bring it back to the overview. In HFSS and SI wave, we did a PI-SI analysis. Then in iSpec, we do the thermal analysis. In mechanical, we are more into the shock vibration, and of course, the thermal stresses can also be captured using mechanical. But when you put everything together and then trying to capture the full lifetime prediction, that is when the Sherlock reliability physics analysis shines. Okay, there are features. There are some very clear benefits that it brings in. So actually, I think I mentioned them several times. A quick summary is that we be able to quantify the different loads and separate them and see which one's going to affect the most to our board, to our design, and also increasing the first parts yields during the manufacturing. Definitely helps reduce the warranty returns in the field. Make sure that your delivered quality meets the requirement even after the entire lifetime, the entire product lifetime. The broad life prediction helps assess the risk, and eventually we are using the best in class modeling techniques, really helped democratize the FEA difficulty for a design engineer. Okay, so this is what Ansys is offering. Not just offering the tools, we also offering a very high quality support along the way that you are developing your workflow, and also helping developing your product life roadmap, for instance, looking into like how you're going to achieve for design for excellence. another overview of different products, what kind of similar, let's say, analysis topics is related to. As I understand, all of the audience will also receive a recording of these slides. So, sorry, of this webinar. So you can definitely look back and then get the information that you need. So that's all I want to talk about today.
Thank you very much, Tim. Thank you very much, Edwin, as well. If there are some people that have questions, I see that we have one. Tim, that's maybe one for you. Is it possible in Sherlock to simulate a stack of multiple PCBs?
That's a good question. I think it could be possible, but I have to double check. So for that question, I think it's better that I double check the details and answer you by email. But in general, the idea of Sherlock is that you simulate a single PCB and knowing like how you mount it, what kind of loads that you can experiencing, and eventually gives you the prediction of that particular PCB. And when we're talking about the stacks of multiple PCBs, then there are some interaction between boards that maybe that's more for the mechanical kind of jobs. But I can definitely double check about the capability in Sherlock in these aspects.
Okay, perfect. I see Danny Audish also has a question. I think I can unmute everyone. Danny, I think you can unmute yourself and ask the question.
Yes, okay, yeah. Is it working?
Yes, it's working. I can hear you loud and clear.
All right, thank you for the nice presentation, Tim. You mentioned with Sherlock that you just have to put in the random vibration spectrum.
Yes.
Is there a library with the other statistical input data, for example?
Yeah, there are some templates, but it's not a very large library. Let's say that there are some templates that you can start with.
And based on which statistical methods is it based? Is there a Weibull, for example, or other data that you need to put in about the materials?
You mean the materials property or what?
Yeah, to predict the lifetime, right? You need to put in material properties that are related to reliability, long-term lifetime.
Yeah, sorry. Yes, now I understand. So the material properties, you can definitely define your own, let's say the material fatigue models, but they are already quite some nice, let's say fatigue models inside. And what's the additional value of Sherlock is providing is that they have a dedicated labs. I believe that's in US, that they are keep testing and then validating all these fatigues models and building some preparatory predictions to the lifetime. So which gives you a very high confidence results based on the combination of testing and theoretical results. If you like, we can send you some more information about the fatigue library that it has.
Yes, maybe that's interesting for us. Yeah,
definitely do it, please.
Okay, thank you.
Yes, you're welcome.
Then we have another question of Huub. Are these sheets downloadable? Do you mean the PowerPoint presentation? Well, like I mentioned, the webinar is recorded, and you will all receive a recording and an accompanying email, so you can always look everything back. Okay. I don't see any further questions. Really don't hesitate to send to info@infinite.nl or support@infinite.nl should you have any questions or should you want to receive any further information. Then all that rests me is to wish you a very nice day and evening, and we'll hopefully see you soon in a talk or maybe in the next webinar. Thank you, everybody.
Yeah, thank you also, Sarah, and have a nice day.
Thank you all. Have a nice day.